Good morning everybody. We have already discussed about surface unit, subsurface unit. These two topics actually almost covered. Now we have two more topics, performance analysis, how to draw dynamometer card or pump card, and how to understand that one. Next is sucker rod, the rod connecting surface unit and bottom hole assembly. In between there will be big rod, long rod. So long rod, how some discussion will do based on our physics and stress analysis. Okay. Before I go into details, I will explain a little bit. Here I got one pumping unit. Actually this is air pumping, this is not water, because I don't want to spill water in the studio. So I took this air pump. So here is on hole. So if I pump it, actually air will be blowing here. Okay, you can see this, how air is getting blown. Okay. You see, when I pumping, this red color is getting blown, right? Okay, so you can assume this is sucker rod pump. Sucker pump is, this is my sucker rod will be there on the top, and this is rod going to the plunger, and there is one traveling valve, standing valve. This is traveling valve. Okay, when I am moving down, it will take liquid. If it is liquid pump, it will fill here, and when it is moving up, this liquid will be going through this. There will be one hole, and it will go through this, and whole system will be put inside one tubing. Okay, and this pump must be anchored, or some nipple must be there, so that when you are pumping, it should, the whole thing should not go move up and down. Okay, and this nipple or holding, bottom anchored or top anchored, you have already gone through that one in previous lecture. So bottom anchored means you hold it here, move your plunger up and down, or you hold here on the top. So the top anchor is here. Okay, and how the plunger assembly, let's open this one. Okay, this is not actual sucker rod pump thing. So here they are using like simple one elastomeric rubber system is there. Okay, this is a plunger, very small plunger for air pumping. This is balloon pumping actually, for balloon blowing. Okay, now whenever you are pumping, this plunger, most probably you cannot see here, plunger is here now. Okay, you can see this distance. Okay, this distance, when it is going directly to here, the plunger is almost touching here. Okay, in actual practice, plunger will not touch this bottom, it will make some gap. This is top dead center. Plunger cannot move more than this one, and plunger cannot move more than this one also. Plunger will be moving this one to this one. This is stroke length. Okay, this is your actual stroke length, plunger stroke length. Now because of mechanical reason, your plunger must not hit the other end. Okay, if it is hitting, because of rod stretch and other issues, the whole system can fail. So there must be some gap. Okay, piston or plunger will not touch, there must be some gap. Okay, so the piston traveling that portion is called swept volume. Okay, some portion must be left cleared. I mean, that area will be filled with, if it is air pump, then it will be air. If it is liquid pump, it must be liquid. Okay, and if your this one is touching, continuously be hitting this bottom valve cage or valve, then whole system can fail. So that's why this some small distance will be this piston will not be traveling. Piston will be traveling only this one. This is called swept volume. So I'll draw this one, swept volume. Now if I draw this similar way, right? Okay, the piston, this head will come up to this level. So some portion will be not traveled. So piston, if traveling from here to here, this will be swept volume, swept. Okay, and if piston is traveling completely, if piston or plunger is coming and hitting this one, so your life will be good, because there will be no clearance volume. This is called clearance volume. If no clearance volume is there, then actually there you will have certain benefit. I'll discuss later why this clear volume, if you make 0, then what will be a benefit. If you do not make 0, then you know that mechanical reason you have to give some clearance. Okay, in performance analysis we'll go through this dynamometer card and pump card. Okay. So what is dynamometer card? Dynamometer card actually it will give force profile. So this is sucker rod. Okay, sucker rod will go, let's say this is my sucker rod, and okay, so this is my sucker rod. When your horse head is pulling it up, that means it is applying force or pressure here on this rod. Okay, so if I put one here, let's say your the airplane luggage, when you check the weight, whether it is 20 kg or more than 20 kg, so that some weight bridge is there, right, weight measuring system. So if you put in between there, okay, so when you are pulling up, so it will show some weight is there. Okay, when you are moving down, again it will show some weight. Okay, so when pulling up and pulling down, it will show some weight changing. Okay, pulling down means low weight, and pulling up means you are lifting all liquid plus this rod weight, friction, other loads will be there, that's why load will be higher. So actually ideal curve should be like this: stroke length, stroke STROK, stroke length, stroke length, and this is load. Okay, so when piston at the bottom, you are trying to move up, so trying to move up, so that time from here to here it is going. Okay, it's trying to moving up means all time your force is higher. Okay, higher force means horizontal load, you have drawn this line, horizontal line. Now you are trying to move down. Move down means lower pressure you are giving, lower pressure you are giving, or lower load you are giving. Okay, so it will be looking like this. So vertical higher force, lower force, higher force, lower force. Why higher force? Higher force means whole fluid column you are lifting up, whole rod weight is there, and there will be fluid friction will be there. Okay, and it is going down, so fluid load will be lowered, and because of rod its own weight, it is trying to going down. So your actual that needle, that weighing machine needle will show lower amount of force or load. Okay, so that's why you get this curve. Okay, this is bottom of the plunger, and you are lifting up top of the plunger. This is top of the plunger, and again when top is there, again you are trying to move down. When immediately moving down, the pressure, the force is changing actually. So again it is top, but it is moving down. Okay, moving down, same force. Again this is bottom. Okay, so when it is bottom, when pushing down, force is something different. When pulling it up, force will be something different. That's why this force is changing, top bottom, A, B, C, D. So A force and B force, that force reversal happening. When it is at bottom, your measuring needle will be showing it is going down, showing lower load, but when it is trying to moving up, again suddenly force will change. So that force will be showing at B. Again when it is continuously moving up, it will be showing continuous pressure or force, and it will be still in top, but force will be continuous. Okay, and again when it is on top, it reached on top, again you are trying to moving down, so that time force again it will be constant force almost. Okay, so that force is changing when it is moving up or moving down. Okay, so this graph will be drawn using some mechanism called dynamometer card or pump card mechanism. So we'll discuss later. Okay, so this dynamometer card called dynagraph. Okay, dynamometer, it will have maybe piezoelectric type system or mechanical type system, where you get force profile of the polish rod, and where you are measuring, actually the measuring instrument will be on the polish rod, because if you want to measure any other place inside the wellbore, it will be very difficult to handle. So people will be measuring on the polish rod itself. A polish rod, you can remember that you have horse head, and there will be polish rod section. Okay, polish rod section will be passing through your stuffing box, right? Then it is going to your actual sucker rod. Okay, so this polish rod section, there will be that force measurement equipment or pressure measurement equipment, how much force it is getting the rod. So that force or pressure or load you are measuring there. Okay, I am saying pressure sometime because force divided by rod area, so you can get pressure also. So this is your stroke length, actually stroke length. This is your polish rod load, so this is polished rod load. So many times we write polish rod load. Okay, now what is happening? Let's say plunger is moving down. When plunger is moving down, your plunger is moving down means travelling valve. Plunger is having travelling valve, right? Plunger is having travelling valve. This plunger is having travelling valve, right? And standing valve is there in barrel. This is barrel. This is plunger. Okay, this is TV. This is SV. Okay, so when it is moving down, the TV is open. Okay, so TV is open, and this is upstroke, this is downstroke, this is upstroke. Okay, from here to here upstroke is happening, and this is downstroke. Okay, and downstroke is happening here. Downstroke is happening here. Downstroke is happening. I should not put this one, I should put like this. Okay, this is head. So when, let's say, it is moving down. Okay, moving down means travelling valve is open, standing valve closed, right? At the bottommost position, first travelling valve will be closing. Okay, TVC. Then it is moving, trying to move up. Okay, then it will open a standing valve. So TVC means travelling valve opening. I'll write somewhere, otherwise you will forget. TVC means travelling valve open. SVC TV open. SVC is standing valve. Standing valve closing. So O means open, C means close. I am using the term. Okay. Now plunger is just going down. So when almost bottommost position, that time instantaneously it will stop actually. So that time travelling valve will close. Again you are trying to move up. When you are trying to move up, that time after few instants, let's say 1 second, after 1 second travelling valve is closed, standing valve will be opening. Okay, so this SVO A B, at B position standing valve is open. Now standing valve is open, travelling valve closed, you are lifting it up, so all fluid will be moving up to the tubing into the surface. Okay, and you reach to top position, you reach to C position. In C position what will happen? You reach to C position, instantly you are trying to moving down. When trying to move down, first your SB will be closed. So first standing valve will be closed, SB will be closed. Then again you further press down, let's say after 1 second, this will open, TV will be opening. Okay, the sequence will be that when at the bottom you are trying to move up, so you are trying to reach bottom, stop instantaneously. So that time this is travelling valve is closed, little bit trying to move up, so that time this cylinder pressure will be lower than this pressure, this will open. Okay, so what is sequence is happening? Let's say I'll draw one picture like this. I have one barrel. Okay, so barrel is having standing valve, and I have one plunger. Okay, so I'll be putting name like A, B, C. So C, actually there will be gap, so this will be C also. This is TV, this is SV. Okay. When you are trying to move up, so initially what will happen, pressure P, I think previous lecture I put P well, this is P cylinder, this is P tubing, this area P tubing. Okay, P well, P cylinder, P tubing. When you are trying to move up, what is happening? You are trying to move up, the P tube is high, very high. Okay, so P tube is high. P tube is high when you are moving up. Now, when you are moving up, the cylinder pressure must be reduced. Okay, when cylinder pressure is reduced, P wellbore pressure is more than cylinder pressure. P well more than P cylinder, then SB open. Okay, you are trying to move up, piston or plunger is the bottom, you are trying to move up, what will happen? You are trying to move up, piston is or plunger moved up, so this area you are trying to reduce pressure, so cylinder pressure a little bit reduced. When cylinder pressure will be reducing and it will be reaching lower than your wellbore pressure, wellbore is here, wellbore pressure and cylinder pressure, so wellbore pressure higher, this pressure lower, so this pressure will be pushing this standing valve and it will be opening, so this valve is open now. Okay, so first what will do, when you are trying to move up, is travelling valve closed, you see top picture, TVC at position A is, okay, I am putting a wrong name, I should put some other name actually, let us say put this one 111. Okay, in top picture you see at A position travelling valve first close, then your SB opening. Okay, then you are moving up, no change is happening, when you are reaching the top, when your this velocity is reduced, this is sinusoidal velocity actually, initially it will be very low velocity, very high velocity, then again it will be slowing down because this is sinusoidal, so initially lower velocity, high velocity, then again slow velocity. So at the middle of the plunger the velocity will be very high actually, because this is sinusoidal, your crank is rotating sinusoidally, right, it is giving sinusoidal force, so that's why initially low velocity, very high velocity, then low velocity. Okay, when velocity is going down, so that time standing valve will fall down, it will close this path. Okay, so it is nearby top, standing valve will be closing the path, so C position your standing valve closed. Okay, now again you are trying to moving down, when you are trying to move down, what will happen, standing valve closed, cylinder pressure will be increasing because you are pushing down. Okay, standing valve closed, you are pushing down, cylinder pressure high, when cylinder pressure high, TV opens. Okay, P cylinder more than P tube, then TV open, travelling valve opening. Okay, when P cylinder more than P tubing pressure, so that time TV opening. So that's why you see this D position in the top picture, TV opens at D, although both plunger is on the top. The sequence is that travelling valve closes, then standing valve opens, move up, standing valve closes, travelling valve opens, and fluid, whatever fluid is there, that fluid is moving up. Okay, moving up. When again plunger is moving up, all fluid will go to the surface to a separator. So this way it is working. But in actual practice, what happens, tubing extension, rod extension will come up. How tubing extension or rod extension will come up, I will explain. Okay, so I assume this one is my plunger assembly, let us say this is filled with liquid. Okay, so what happens, let us say this is plunger assembly is it is inside one barrel or cylinder. Okay, so plunger will be moving up and down like this. Okay, and there will be travelling valve, standing valve, and plunger is having its own weight, rod will be there, so it will have their own weight. So what happens, when you are moving it up, and rod, although it is metallic, but still it will be stretching because very long rod and weight is very high, that's why it will be elongating. So the term they use stretching. So what happens, that's why I put this one actually elastic thing. So I am assuming rod is elastic, so I put this one elastic just for demonstration. So plunger is here and when piston or plunger is the bottom and you are trying your horse head, and horse head is trying to move up. This is, assume this is walking beam, my hand is walking beam, this is horse head, and horse head is trying to moving it up. So when it is trying to moving up, so first rod stretch is happening, you see, then after that only it is lifting up. When it is going down, again rod compression will be there. So rod will be continuously compression decompression will be there, okay, compression decompression will be there. And if it is slow speed, then slowly rod will be stretched, but it will not having any wavy motion. But if I have very high speed, for example, I am moving up like this, so it will have this much of effect, okay, because rod is elastic, okay. Although if it is a short length of rod, you actually you cannot see that elongation, but if you have 1 kilometer, 2 kilometer, 3 kilometer long rod, or 3000 feet, 4000 feet, 5000 feet, so in that case the elongation will be sufficiently significant. So because of significant elongation, actually when your beam pump, your polish rod is moving, let's say 2 meter or 6 feet, your actually plunger is not moving that much. Plunger or this pumping system, plunger is not delivering that much fluid because the rod is elongating. You can see this from hand to this, how much it is getting lifted. Let's say this is bottom of position. Now your horse head is trying to move it up. So when it's trying to move up, you can see this, it is stretching, then it is lifting. So although it is moving maybe 2 feet, but actually horse head moved 4-5 feet, okay. So actual the stroke length on the surface will be different from actual stroke length in the well bore, okay, because of this rod stretch. Another thing happens when you have a tubing and tubing is not anchored. So you have seen that tubing can be anchored, non-anchored also. So what is tubing anchoring? Tubing anchoring is like this: you have one casing and you have one tubing, okay, and you have bottom hull assembly or pumping system, like pumping system is here. Pump will be nippled here, okay, it will be properly holding here on nipple, right, we use the term nipple, okay, bottom holding pump, bottom anchored, or you can have top anchored also. Bottom anchored means you are holding here, top anchored means you are holding somewhere else. This is this is cylinder, we can assume. So cylinder must be hold here, otherwise cylinder when you are moving it up and down, it will move up and down like this. So better you hold it here or hold it here. So it can be top anchored or bottom anchored. Now tubing, this cylinder will be fixed with tubing, okay, and tubing must be fixed with your casing, okay. This is your casing, okay. So tubing must be holding by something here, otherwise tubing will be just hanging like this, tubing will be hanging like this. So if we have bottom anchored tubing, then sometime it is good. If we don't have anchoring a tubing is just hanging. If it is hanging, then tubing will be elongating, its length will be changing because it is also very long tube, steel tube. So long steel tube means it will be elongating, or it will have like elastic property like this, okay. Now you put your bottom hole assembly and fix the tubing, you hold it, and when you moving up, you are giving very high force, okay. Because of very high force, tubing also will be having little bit motion. Again when it is going down, tubing also will be elongating. So because of its own weight, tubing will be elongated already, okay. And when you are moving it up, your let's say I'll draw one picture here, okay. So you see this pump locations, pump bottom location in the figure. Because of this upper pull, tubing will be shortened little bit, okay, because tubing is fixed with this one. So when you are pulling it up, plunger, so plunger is pulling up means fluid friction will be there and whole fluid column, so whole load is getting reduced on the tubing. So tubing will be little bit shortened, and when again you are moving it down, tubing will be elongated little bit. So every time tubing will be elongating, non-elongating. But if you have anchored tubing also fixed on casing, then that movement will not be there. So anchored tubing, non-anchored tubing, you know the difference now. If you have anchored tubing, there will be no tubing motion, elongation. If you have non-anchored, the tubing also will have move. Then our Dynagraph card or Dynagraph the figure, that will be different if you have anchored tubing, non-anchored tubing. Another case is that when you have sticking tubing, if you have tubing sticking barrel or sticking rod, you have tubing this rod, sucker rod. If you have sucker rod sticked, okay, when you are lifting it up, you need very high force. If it is freely moving, then certain amount of force will be required, you know, calculated force. But because of certain reason, because of bend or some problem, it is sticking. Then on the surface, your needle weigh meter reading or piezoelectric type of measuring device, that will show higher reading because it is getting stuck somewhere. Okay, in some cases there may be some leakage here in plunger. Okay, this barrel, if barrel is having leakage, then when you are lifting it up, fluid will be leaking out. So that time you will be requiring less amount of force. Okay, sometime your traveling valve is leaking, sometime your standing valve is leaking. Sometime there will be friction due to fluid, sometime there will be friction due to maybe tubing is rubbing your sucker rod because of the crooked well bore. Crooked well bore means normally we assume the well bore will be completely vertical, but well bore may not be vertical, it may have length like this. Okay, so in that case rod can be rubbing somewhere sometime. Sometime there will be gas filled area. If it is gas filled, then when you are compressing, when it is moving down, gas will get compressed, PV equals nRT, right, PV per gamma equals constant. So when it is going down, it is filled with gas, going down, standing valve closed, traveling valve will be opening when cylinder pressure will be more than this delivery pressure, upper pressure or tubing pressure. Okay, so you are trying to move down, because it is gas, it is getting compressed, pressure is not developed properly because it is getting compressed. When pressure will be sufficiently higher than your delivery pressure or tubing pressure, then only your PV will open. Okay, so that gas compression will have problem. Another possibility will be there, intake pressure is very low. Because of low pressure, this is not failing actually, and the cylinder pressure is also very low because of inlet pressure is very low, because fluid column you are not maintaining, because that net positive suction head, that entry pressures, there must be some entry pressure, so that fluid will be entering, it will be opening the standing valve. But if your entry pressure is not sufficient, what will happen? It will try to suck something, but nothing is there. So what will happen? It will create very low pressure. Okay, water vapor also can be created. And when piston is moving down, it is moving down. So because of low pressure, it will be moving at very high rate. If it is filled with liquid, what will happen? It is moving down, liquid will be opening your TV opened, it is moving down smoothly, liquid is going up, but there is no liquid, very low pressure is there. So when it is trying to move down, there is no resistance of liquid. Okay, no traveling or opening, so it will be moving at faster rate. And when the fastest rate will be there, middle of the stroke, I told you this sinusoidal, no? So at the middle of the stroke, speed will be very high. At that middle of the stroke, speed very high, and if it hits the water or liquid surface, it will be hitting. When it is hitting, suddenly these joints can break, or it can create wavy motion, and that will be rubbing your tubing, that can fail. So how can you sense that? So from surface Dynagraph curve or card, you can understand that one. Let's see what are the different types of Dynagraph curve. So there are several idealized Dynagraph curve people have designed or understood, and this curve, proper understanding of the curve, it requires lots of experience. Okay, experienced engineers, they have devised certain mechanism to understand some properties of the curves. So if I have ideal curve means it will be like completely rectangular shape. Okay, this is stroke length, and GTH, and this is PRL. Okay, and this is actually counterbalance mass. Counterbalance. So counterbalance, already you know that counterbalance will be storing energy and it will give energy. So this is average force how much required in counterbalance mass. Okay, so when it is going downstroke, the energy will be lower, and it going upstroke, energy will be higher. Okay, that's why it is some portion will be below the counterbalance line, and some portion will be above the counterbalance line. And you know already this is downstroke, this is upstroke, and A, B, C, D. This is ideal. Pump is completely full and there is no problem. Okay, and dynamometer curve, actually two things are there. When if you are measuring, if you are putting dynamometer curve instrument here, so this will not show your rod stretch or tubing thing, it will be showing only the pump related information. Okay, but the same machine, if you are putting on the surface where your polish rod is there, so polish rod will be telling all the stories of rod, pump, tubing, fluid. Okay, but if you are putting same machine here, you are not getting that rod stretch or tubing stretch or leakage in tubing or fluid friction. So all this part will be removed, so it will be more idealized. So this curve actually will be resolving more on pump side. If you want to understand the surface side, then that will be more complex actually. So first understand the simpler one, then we will go to complex one. Okay, so pump is full, there is no problem in any system, so your life is beautiful. Now in some cases you have flowing wellbore. In flowing wellbore actually you are not giving any pressure, so pressure will be lower than the requirement. So this will be flowing wellbore. Okay, flowing rod no, yeah, so it is not getting any fluid load. Okay, so your the dynamometer, whatever putting on the polish rod, it will show negative. Okay, the next is bend or parallel sticking pump. Okay, ideal pump will be like this pump curve, but if you have some sticking, let's say when plunger is moving up, somewhere it is getting sticked. Okay, my pump is like this. Okay, plunger and barrel assembly like this, and there is something problem is here. Okay, so when it is moving up, at certain moment you need very higher amount of energy. When it is moving down, again your energy is getting changed. Okay, so the curve will be looking like this. Okay, so extra problem we are adding. If you have sticking barrel, bend barrel or sticking pump, bend or sticking pump. Okay, now pump sticking up or down. So in this case, okay, so pump sticking up or down. So what is happening, when plunger is moved down, you are trying to move up. When trying to move up, it got stuck, because of that higher amount of energy will be required. Okay, and when it is moving down also, same thing will happen. So the curve will be altering like this. Okay, two spikes will come at the end. Next is gas interference. If I have gas here, as I told already, this is closed, this is closed, now this is half filled. Okay, this cylinder is half filled, this much of water is there or liquid is there or oil is there, and this is only gas. So the curve will be changing like this. It is like this, it will be compressing, PV power gamma equals constant. Okay, okay, so gas interference, and when it is moving, gas is getting compressed. Then once compression done, then liquid will be entering into your this area. Okay, then when you are moving it up, still there will be some remaining gas, so the gas will be again expanding. So that expansion is showing this curve A, B, C, D. You see B area, it will be having some smoothness will be there because of gas expanding. C to D, there will be compression. So PV per gamma, that approximately that formula it is following. So it will be curved actually. Okay, so at this time actually you are getting production, but it's not a pump off condition. Pump off condition means you are not getting any pump delivery or flow, because of gas is filled inside, it is gas filled, there is no liquid, so it is not pumping actually. So that is called pump off condition. So in that case you have to stop the pump for a certain time, or if you are thinking that lots of gas coming, so you slow down the pumping speed. When you are slowing down, what is happening, you are slowly you are allowing leakage and other things, so that gas lock will be lower. Maybe your intake pressure is very low, so fluid liquid coming into wellbore is very low. So in that case you slow down or stop pump for certain time, allow liquid column to build up, then you pump. Okay. Next is tubing extension. Okay, when you are lifting up, tubing also moving it up. So actually your beam pump horse head is not giving so much energy, because tubing spring constant, that is also helping to lifting up. Okay, so your actual force application is lower. Okay, so it will be slowly moving, it is helping tubing contraction. Then it will look like this. Okay, A, B, C, D. So A to B it will be tubing contraction, and C to D again expansion. Okay, this will be like K. K is tubing spring constant. Okay, and this is tubing extension, tubing elongation. Okay, tubing elongation is there, then curve can be like this. Another possible fluid friction. If you have very narrow tubing, then when you are lifting fluid, so fluid friction FLV square by 2GD, right? You can remember fluid friction formula, del P equals FLV square by 2GD. So that formula, pressure drop will be very high. So in that case the curve will be changing its shape. How it look like? First you draw the ideal part. Okay, and because of fluid friction it will be like this. Okay, so because of fluid friction, okay, why this center part is higher, showing higher force? Because I said like it is sinusoidal curve, right? When this plunger at the middle position, that time fluid velocity will be very high. When fluid velocity very high, if you see the formula FLV square by 2GD, V is higher. When V is higher, your pressure drop is higher. So that's why you are getting expanded bulged curve. Okay, so that time you are giving more energy actually because of fluid friction. So you have to design tubing also properly, so that you get lower fluid friction. Next is crooked well. So if you have crooked or bent well bore, again your curve will be changing. Okay, so bent well means a rod is sticking, is rubbing. Okay, because of bent tubing, rod is rubbing, so you are giving actually more energy. When going up, going down also, it will be taking more energy. So this is crooked well, crooked or bent well. Okay, and split barrel. Split barrel is like this. The curve will be coming like this. Why it is looking like this? Let's, when it's moving up, okay, moving up after certain time, because of high pressure, this there will be leakage here. Okay, because of leakage here, your pressure will be dropping. So suddenly the pressure is dropping here. That's why this is barrel leakage. When pressure is lower, so that time maybe leakage may not be visible, but after certain time the split will be visible. So that time the pressure fluid will be coming down to the other area. Okay, then pressure will be down suddenly. So that is called barrel leakage. And next is fluid pound. Okay, gas interference we have seen. Now we have to see fluid pound. What is happening in fluid pound? Fluid pound, it will go like this, it will go like this, suddenly it will come like this. Okay, fluid pound. What is fluid pound? I already told that when piston in the top is going down and there is very low intake pressure, because of intake pressure inside this chamber pressure is also very low. Because of chamber pressure very low, initially going down, this low pressure is getting increased, small gas also will try to compress. Then when it is in the middle of the stroke, the velocity, plunger velocity very high. At that time, if you face any liquid surface, then it will be hitting on the liquid surface. When hitting, vibration will go on. So that's why this curve is going like this and suddenly pressure changing. Okay, so that is called fluid pound curve. Next is worn standing valve. So if we have standing valve worn out, what will happen? Standing valve means this valve, lower one. Okay, when you are moving down, it is leaking actually, it is not closing completely. Okay, so when moving down, it is not closing, so you are losing pressure continuously, you are reaching certain value, again your pressure increasing. Okay, so you are moving down, leakage, again moving up, leakage. So it is not filling this system properly and you are losing energy. Okay, this is worn out standing valve. Standing valve. If I see worn out traveling valve, then figure will be like this. Okay. Now in any well bore, you cannot get these pictures isolated. There will be mixture of things. For example, maybe you have bent barrel sticking pump with your gas interference, or you have tubing elongation with crooked well, barrel leakage with maybe one standing valve. So it will be mixture of figures. So it will be, there will be several hundreds of combinations actually. So that to understand that one, actually you have to get good experience, then you can understand, okay, this may be possible. Okay, otherwise so many combinations are there, only getting on these pictures will not give anything. So but you have to understand this is the basic part. Okay, factors affecting the dynamometer card. You see I have listed several factors. One will be speed of pumping and depth. Let's say if you have slow speed, I told already, slow speed, then there will be no wave actually. Okay, if I have high speed, then what will happen? High speed means you see this motion will be there. Okay, and fluid condition, fluid like if you have different bubble point like two phase flow, single phase flow, or it is having corrosive. So all these properties also you have to know to how it is affecting the dynamometer curve. Abnormal condition, the pump, friction factor, how much friction factor is there, fluid friction factor. Pumping unit geometry also important, because this formula normally it will have pumping geometry, and gas law condition is there or not, loading condition, abnormal loading condition is there, crooked well bore is there or not. So all those parameters will be affecting your dynamometer curve. So first you have to understand the basic shapes, then you have to mix it to make complex shapes. Okay.